and welcome to the Inline Ter and Data Functions with Spotfire webinar. We are very excited to have all of you folks joining us from all around the world to be with us today. This webinar is part of the joint webinar series, The Building Blocks of Data Science, conducted by TIBCO and our partner, Roots.ai. Before we begin, let's start off with some introductions. My name is Bipin Singh. I am responsible for Spotfire product marketing here at TIBCO. I'm joined today by Jason May, who is a data scientist at Roots.ai and will be the main presenter. Just as a reminder to the folks here that this webinar is the third webinar in a 5-part webinar series, The Building Blocks of Data Science. In this webinar series, we are taking an educational approach to cover various topics around data science that become progressively deeper in nature with each episode. In the first and second webinar, we covered getting started with data science using Spotfire and Statistica. If you haven't checked it out already, feel free to go to the link listed here and check out the on-demand webinars. In today's webinar, Jason is going to introduce us to some very cool ways of solving data science problems using Spotfire. Before we begin, I can see that some of you are not existing Spotfire users. For those of you who are not very familiar with Spotfire, as a brief introduction, it's a very general purpose analytics platform that is very easy to use and lets you uncover insights faster for rapid decision making. Not only it's an excellent visual analytics platform, but it also has very sophisticated data science capabilities, both built-in and extensible capabilities. You can download a free trial from spotfire.tibco.com and get started today. With that, I would like to hand over to Jason, who will take us through the rest of the presentation. So I'll stop sharing my screen and Jason, you're the presenter now. Please go ahead.
Okay, thank you. All right. You see my screen? Bipin?
Yes.
You can see my screen?
Yes, all good.
Okay. So, hi everyone, I'm Jason May at Roots.ai. I'm a junior data scientist. And at Roots.ai, we are an analytics and innovation company for data science. We have a partnership with TIBCO, and we work up, a lot of our products are in Spotfire, so we are constantly using it and trying to help, develop the Spotfire environment and education. So what we do is we have products which are templates and extensions that help the user kind of advance their Spotfire capabilities. So with that, I will get into talk about data functions and Inline Ter. We have been posed a business question, do seasons affect my business? And we will use a couple different data science methods. We will use lowest smoothing to kind of represent those trends and seasonality in the data and to detect it. And then we will use the Holt-Winters method to account for the seasonality when forecasting. And to do these things, we will be exploring how we create data functions, Inline Ter, and expression functions in Spotfire. So, data functions are really the opportunity for you to take the next step in Spotfire capabilities and go into some advanced analytics. And so, these data science methods are an example, but data functions are the gateway. So once again, our question, how does our small business account for seasonal patterns? We might kind of know, we're small to mid-tier business. We have around 10,000 in sales per week, but we know we have December coupons and, holiday shopping raises our sales every year. So, how do we take that into account? How do we visualize it? How do we represent our data? And, what do we do with that information? So, how to fit a curve is we will use lowest smoothing, and then lowest smoothing can help us draw a curve, but then how do we forecast it into next year? And for that, we'll use the Holt-Winters seasonal method. So first, a little about low-S smoothing. Low-S stands for locally weighted scatterplot smoothing. As you can see here, it doesn't necessarily have to be a scatterplot. It can, you can smooth a line curve also. So the point is, like linear regression, we're trying to draw a line that represents this data on a whole, that summarizes it. So the difference is linear regression tries to create a line that minimizes the error between the line and the actual points of data for the whole data. Now, instead, low-S is going to try to do that locally. So it'll take this data into pieces and then only try to fit a line for these local neighborhoods. So we're looking for a local relationship between the response and a predictor variable over just part of the data. So in addition to the local aspect, we also have the weighted aspect. So even within these local neighborhoods, we're going to have the closer observations to a data point will be weighted more heavily. And then another big aspect of low-S smoothing is it's non-parametric. And I can't stress this enough, because one of the big assumptions of linear regression is that we are working with a normal distribution. But, you know, obviously this data is not normally distributed. Over here on the left, it is, you know, way lower value and has a lower distribution than over here on the right. So that's why linear regression is not a good candidate for it. And, you know, the normal distribution is not an assumption with low-S smoothing. So the final thing on this slide is a smoothing parameter, and the smoothing parameter goes from 0 to 1 and determines how much smoothing that we actually want. We can have 0 is basically perfectly fitting the line, and 1 is almost like just taking the mean in a straight line. So we've talked a little bit about why low-S smoothing, but here I wanted to visually represent it. With the green line, we see just the mean of all the data points taken together. With the blue, we have our linear regression line. And once again, that's minimizing the error between the line and points. And you see how red takes into account, basically what we're having is a piecewise fit of a bunch of tiny little regressions. Well, tiny, it depends on how much your smoothing is set at, but a piecewise fit of multiple regressions, and it is able to then follow the data more closely. So as we said, non-parametric is a strength. Also, the flexibility is good for polynomial distribution. When you see your data go up and then down and then up and then down again, that's a polynomial distribution. And so, you know, low-S is really good at capturing that behavior. And it's robust against outliers. If you know, are only looking at neighborhoods and not data that are in other neighborhoods, you know, an outlier is confined to that neighborhood for having an effect. And then also the weighted nature makes it not have as much of an impact on farther data points. However, of course, with strengths, there's also drawbacks. The smoother parameter can be a little bit subjective. It's susceptible to overfitting because humans are setting it kind of how they want. And also, since we are piecing this into multiple little regressions, it can be computationally expensive. You know, because you're breaking it up into smaller sets, you need larger samples, and it can be, you know, it doesn't have that nice, simple equation that linear regression has. So here we see the function, the low-S function in R. right here, we have in the blue box, we have where you input your data, and it can either be a 2-column data frame or it can be 2 different vectors. And then the green box, we have our smoothing parameter, once again from 0 to 1. And then the last 2 boxes, they relate to kind of the trade-off between precision and how deep we go into the fit and the speed of the model. So now we've looked at low-S, we will take a look at how are we going to get that into R and how are we going to utilize it through data functions. So TERR is the engine that supports R and Spotfire, and you're going to run the script through that. So you will go to Edit, Data Function, Properties, and then you'll register a new one here, or you can insert an existing data function, and again, you can edit your script here. So when you go to start a new script or you edit your script, this is where most of the magic happens. This is where your actual R script occurs, right here in this box. And then also you can set up your input parameters and your output parameters here. I like to think, going over the material, it occurred to me that, first of all, setting up data functions is all just about your connections. It's similar to plugging in, a cable box into your TV. It's all about getting the right connections into the right place, and then you might need on your remote control to then access that, in the right input. So you can think of inputs and outputs as your gateway. So it's your gateway from your script to Spotfire. So coming in, you will name your input something. We like to say simple and just call it input sometimes, and same with output. And that's just a label for our gateway and how we will call it in our script. Now, once we have our gateway set up to connect to our script, we will then go into edit parameters. This was in the same screen where you go to edit data function properties and you saw the register new and the edit. You also see an edit parameters button. And this is where you connect that gateway to the actual Spotfire data. So in this example, the input parameters are called varsim, var iter, and portfolio. So that would be the input and output we just saw. And then here is what the data table is called in Spotfire. So you might have well data, sales data, housing data, or here it's just called input data. And then there's lots of different options depending on which input handler you have, but you can create, columns or which document property, et cetera, to connect to this input. And it could be a value, it could be a data table, it could be lots of different things. Oh, and going out, we have the same issue. You can either take a data table out or you can append the rows or columns. Now, finally here, you can refresh function automatically so that anytime you change something, it will constantly update your function. And then down at the bottom of this, you might see marking and filtering checkbox, which allows the data function to obey marking and filtering. And to me, that's one of the really, really cool things about Spotfire is the interactivity. And the fact that you can limit by marking and filtering in a data function, it allows me to just, I can run a model, make it as complex as I want, and then I just change it based on, different data types, different data tags, different classes. I can just run these exploratory models at the push of a button, and it makes my job so much easier because you can get it with that speed. So I think that marking and filtering is a key function. So that's data functions. Now we're going to look at Inline Ter. Inline Ter is basically doing something very similar to a data function. It's running that same code. It's just doing it on a smaller level. So anytime you might have, you know, a piece of quick code, a one-line function, and you don't really need the data to come out, you just want it to come out in your visual. Inline Ter would be your guy. You can do it straight from a visualization, you know, custom expression. So here's the terminology. It's always going to be output, and then it's always going to be input 1, input 2, etc. for however many inputs you have. And once again, think of this as the gateway getting from your code to your data in Spotfire. So right here is date and price. That's my input 1 and input 2. And the input is my gateway taking it back to this low-s function. And the output is just whatever it outputs. However, at the end of the parentheses, we put a $y. That's just to call only the y column of the output, which is the prediction. Now, that highlights an interesting fact. You can only, you know, output one column. You can't output a whole data table. So that's what differentiates Inline Ter from data functions. This is for quick and easy functions, whereas data functions you can do a lot more, add a lot more complexity. Expression functions, similar to Inline Ter, you can only have, like, you would do this to output a column or an expression. What this is really good for is when you have some sort of repeatable, you're grouping together a series of steps, doing it over and over, a series of, you know, calculations, you might combine them into one expression function. So you name it. The description, this is really cool because whatever is here will show up, you know, in your expression window or your calculated column. So you can put examples so people that, you know, might be using your DXP will know what that function does. So here we have the actual function. This is just like an R function. You have a function, X and Y, and then inside the brackets is we're doing stuff and we're calling these X and Y parameters. And here's kind of more for the Spotfire purposes, here's our output, calling this function, and this is mapping. Remember, it's a gateway. Inputs are a gateway, so it's mapping input 1 and input 2 to X and Y. And then on the other side, once you're in the custom expression, you will put in your, you know, date and price or whatever your inputs are to connect them. So there's our brief explanation. Now we're going to take a look and use these data functions and Inline Ter and expression functions to look at our, you know, our small business sales data and try to display the seasonality. Okay, so here is our sales data. It's just, I simulated it and created a spike in December. So it might not be, you know, you might not see a slow build up to December, but it's just for exhibition purposes. So we just have month in sales is all we need. And then the lowest output will give us, we can ignore this X. What we're interested in is the Y, which should be, you know, in the same neighborhood as the sales data, because this is our fit. This is our prediction of what the data should be. So this is how it looks. The blue is the sales data. We see these big spikes in December. And we also see this green line try to approximate the ups and downs, the variation in the data. You know, it has a little trouble with the peaks, but overall, this is a lot better representation than, you know, linear regression or a mean could do. It sticks with these trends a lot better. So we're going to look at it in the actual data function. So we go to edit data function properties. This right here is where we would register a new data function and save it, which we've already done. And then once you've done that, you still need to insert it. So you would insert it here also. And then now we need to edit it. So we're looking at that low-s data function. And, you know, you name it up here. You might put packages, which we didn't need to. You might put a description for other people. But here's basically my script. My input is input. My output is output. Simple enough. And just to separate it, for clarity, I'm going to rename it my DF. And so then I'm going to do a bunch of stuff to my DF, and then I'll output, you know, my DF and the stuff I've created. So you can also, I have this here to show you could do it in one line. When you call this input, you don't have to name it anything. You can just call it this, and it's going to be whatever that Spotfire data that is mapped to our gateway. It's just going to come out here, whether it's as a value or a data frame or whatever type. So to look a little more on the data science side at what this low-s curve is doing, right here we have 0.1 is our smoothing parameter. So I can change it to 0.5, and it goes, we see, almost to flat. So that's really smooth, and that's defeating the purpose of smoothing. So let's try 0.05. So seems like that line disappears, but really they're just overlapping. So 0.05 has given us a perfect approximation of the data, which again defeats the purpose on the other end of the spectrum. We don't want a perfect fit. We're trying to summarize the data to get a better look at it. So let me switch back to 0.1. So that's how you can just, like, very simply put in, you know, your two variables and then have a smoothing parameter. There are the other parameters that you can use, but for this exercise, that's just how you can simply make changes. Now remember, we had to also connect our data to that gateway. So here's our gateway, and here is our Spotfire data. So in this case, it's our sales data. I can go in here and choose which columns of that data table I want to input, or I can just take it all in. And, you know, likewise, an output table, I can specify, right here, you create a new data table. You would do this the first time and specify the name. And then after that, it replaces the existing data table because, you know, every time you run a model, you don't want a new data table. You want the same, the data table to be named the same thing. So you can also output it as columns or rows. Rows is really useful when you have like weekly updates and it's the same data structure and you just want to add, you know, a bunch of new observations. Then you can always just update the rows. We also here see where we refresh automatically, and down here we see the limit by marking. So that is data functions in a nutshell. Feel free after to circle back on some questions on, you know, how to make that hookup. So now we'll move to Inline Ter, and it is much the same. It has much the same functionality. It's just a different way of getting there. So we're going to do it from our work with it from our custom expression. You see that we've called Ter real here. You know, we have all inline Ter for all these different data types. Again, if you remember from the presentation, this is always going to be output here. and then your inputs are always going to be 1, 2, 3, etc. So that lowest function that we saw in our data function, it calls next variable, which will be input 1. It calls a y variable. Then this is a parameter that you choose on your own. So this is not data coming in. It is, you know, our chosen smoothing parameter. And then we're only outputting one column here, y, which is our prediction. And then here's our input 1. So this is mapping to our gateway input 1, which is then going into this lowest function. And input 2 right here. And so that's pretty straightforward. It works, you know, like a lot of other Spotfire functions, and the documentation is very good right there. So this is the output for that. Now we have a third, we have we have expression functions. You get to those by going to the same place as data function, and it's just a tab up here. So you would create a new, but we're just going to edit. I mentioned here this description will come up in the calculated column window or the expression window. And here's, you know, the script that we have already walked through. So once you create that, then you would go to, say, create a calculated column, insert. I've already inserted it, so I'm going to just edit it. So you do it just like you would with other expressions. But see how cool this is? We've made our own data, our own function. So this is just like any other function that's built into Spotfire. We've made our own function, and we can call it anywhere we want. So we call lowest expression, and like I said, we can call it here. And whatever we put in that expression, however much documentation examples we put, is there for anyone to see. So, you know, it's some really neat stuff there. And we see the month, this is input 1, that's input 2, and those map back to input 1 and 2 when we set it up, which then of course map to the x and y called in the R function. And so you have your column, and this is created from a calculated column. So if you haven't caught on, all three of these things have done the same thing. All three data functions, Inline Ter, and expression functions have done the same thing. It was just a different way to get there. And when you utilize when you utilize them will determine when you want to use which one. So if you want the data to come out and be in data tables, you need to use a data function. If you just want it quick and dirty and you want to just put it in pop it in a visualization, Inline Ter. If you want to use it as a bigger function that you might use over and over and over and within other expressions, you might look to use it as an expression function. So with that, we want to notice, excuse me, let's go back to our business problem. We've showed how low S is good for, you know, these localized trends. So it going up and down, it's good at capturing this local information. However, and it's good, you know, if you're looking at it using 1 year, it's probably a pretty good approximation, because you wouldn't want it to go all the way up because you might think this is an outlier, right? So it's just good at looking at it, you know, a trend. And when we talk time series, there's a distinction. There's trends, which are whether, you know, the general data go up or down over time. And then there's seasonality, which is when the data behaves in a certain way, when it goes up or down at a certain time in a certain period. So that's seasonality. So you have trends and seasonality, and low S has proved to be good at trends. But when you see these things happen year after year, it should now be approximating that seasonality better. So for that, we go to Holt Winters method. And this can get pretty complex. So we're not going to go into the nitty-gritty details. We just want to show you that, what's out there for kind of advanced analytics using data functions. So the Holt Winters method, it's also called triple exponential smoothing. So the first exponential smoothing accounts for all the data as a whole, like it's looking at all the data at once and smoothing based on that. The double exponential is that trend that we talked about, which is the trend upward and downward. And then the triple exponential smoothing is accounting for that seasonal variation. So what the Holt Winters method is doing, it's really cool. It takes all that seasonality and all that trend out of the data, then it makes a prediction, and then it throws those trends and seasonality back into the data. So instead of, rounding off these curves we see here where at the end of the year it's back up to this peak. So let's take a look at how that would work, and let's forecast next year's sales. So Spotfire has this already built in where you can forecast, and that uses the Holt Winters method. You see, this is our line predicting our seasonality, and these are confidence intervals. We can edit this in lines and curves. And you can make a lot of decisions on the level, basically those 3 exponential smoothing factors you can customize through lines and curves. Now, what it doesn't quite give us is our data tables. And remember, that's the great use of data functions. So we were able to go in, create a Holt Winters data function, and there's a lot of data manipulation I did to join 2 tables down there, but really the Holt Winters is just right here. You need to change it to a time series data type, tell it when to start and how much per period that happens, and then you run it in the model. There are lots of more parameters that you can use here, but I wanted to keep this simple. And then, so you have your model, and then you forecast based on your model. So you would predict, and you can predict 12 ahead, or you could do 3 years, you could do only 3 months if you just wanted a quarter. Again, there are lots of different parameters here, but just right there is what gives me this right here. These are our predictions for the next 12 months. We have our fit, we have our upward, lower, and confidence level. And then I joined it together with the previous data so that we could have, a comparable visual. And then right here you see is where the predictions start. So it's a little different because the parameters are different, but you can achieve the best of both worlds of getting the visualization and getting the data using Holt Winters. So that is the main part of my presentation. I wanted to tell you a little more about some of the tools we have. So we have this data, we have what are called extensions, and they come up in the toolbar just like a data relationship or a regression modeling tool that are native to Spotfire. Our extensions then come in right next to those, and it gives you, all these different functionalities. In this case, it's a data science extension. You can do all this exploratory data analysis, like QQ-plot and histogram, and a data summary that's more in depth than maybe in the summary table. You have PCA for dimensionality reduction. You have things like training sets and model evaluation that really is meant, you know, you're learning these concepts, these data science building blocks, and there's a lot of tedium and man hours that go into just kind of building these visualizations that to do this analysis. And so we're trying to grease the wheels and, you know, get it so you can do it with a couple clicks of a button. So last words, you know, you can stay up to date on your Spotfire on our blog, Data Shot Talk. We have lots of tutorials on how to do things, and we also have just general data science discussion. So I'd recommend you go check that out. And then also, you know, be part of our Spotfire community. Tibco has some great templates on Tibco Exchange. We have all our templates and those extensions I was showing you on exchange.ai. That's our marketplace for Roost AI. So go check them out. If you have any questions on, you know, how you might utilize one of those, an extension or a template, or, you know, questions from the talk today, don't hesitate to email me at jason.may@roost.ai or support@roost.ai, and we'll see if we can help you out.
Thank you, Jason. That was a great presentation. So if you have any questions, you know, feel free to enter them in the Q&A panel on the right-hand side, and we'll try to answer as many questions as we can. So here we have the first question. So, Jason, the question is, in the lowest smoothing, you showed the smoothing parameter. We used a value of 0.1. So what does that mean? Is that related to the probability of something happening? Like, for example, 0.1 would reflect a probability of 90%. Is there a physical significance of that smoothing parameter?
Yes, that's the percentage of the data that's in your neighborhood. So, you know, your data will only be affected by 0.1% of the data when it's the parameter is set there. So it's defining a local neighborhood.
Very good. There's this question about the data science toolkit that you mentioned. So does your data science toolkit offer any mathematical optimization tools? If so, what?
Mathematical optimization tools. So we have, I mean, not specifically. We have the PCA, which does a principal component analysis and helps, you know, with dimensionality. But no, we don't have any like optim functions. But that's a great note. We'll look into it.
There's a question about the version of Spotfire that you're using. So what version of Spotfire are you using? I have not seen the forecast option and also not the data science tool.
I'm on 7.7. So I don't know. Vibin, you might know better than I when the forecast was put out.
Yeah, all the recent versions, even 7.7 has right-click forecast built into it. I don't remember the exact version number, but it was quite a few years ago. At least more than 2 years ago, I could guarantee that. So whenever you have a time series data, if you right-click in the chart, you should be able to see that forecast, the built-in forecasting option. Cold winters that you can further edit and get more control over all the parameters that Jason showed. And regarding this data science tool, this is of course, you know, an extension capability from roots.ai. So that's what we were seeing. The question is, will you publish the example file that you went over in the presentation for download? Jason, could you help us, you know, where would this be? Would this be on exchange.ai or?
I can definitely publish it on, yeah, we can publish the template on exchange.ai, and so we'll do that. in the next couple of days, and I can, or is there a follow-up email on?
Yes. Yeah, there
okay.
is a thank you email going on, so we can include the links on how to download the data set and the DXP there as well.
Okay. Yeah, perfect.
Okay. And so the next question is, you mentioned Markov Chains. What about that?
I don't think I mentioned Markov Chains.
Yeah,
they
I don't
were not related.
Yeah, okay. How would you validate the parameters for the prediction model by looking at historical data as a trial? What is the evaluation parameter to demonstrate the accuracy of the prediction model?
So, you know, simply you could, you know, just use a train and test set. And like I said, the data science toolkit is a really simple way to divide your data. And you could divide it into 80-20, 70-30, 90-10 are kind of common values. And so you would, you know, basically try different models at different parameter sizes and do it on your training, and then evaluate it on your test using probably, you know, RMSE, mean squared error. And you just see, you want two things. One, you want to see the data perform well within your training set and your test set. You know, you want the lowest RMSE, but you also don't want to see a big swing. So it's always going to get slightly worse in the test set. And you just don't want it to have to be, you know, a wild swing. Now, the other thing you might do is cross-validation, which is a little more complex, where you divide, you know, your training set into 5 or 10 different data sets, and then you evaluate your parameter on accuracy based on each of those within the training and the test set.
Thank you. So I guess that was the last question for the day. With that, I would like to thank you very much, Jason, for this amazing session. And please don't forget to sign up for the 4th webinar in this data science series, webinar series, and talk to you guys later. Thank you. Bye.
Thank you all.